A PEM electrolyzer stack fails after just 12,000 hours. The project expected 80,000. Hydrogen purity begins collapsing unexpectedly. Cell voltages rise across the stack. Thermal instability appears near the center of the active area. Operators shut the system down. Engineers disassemble the stack expecting to find a single catastrophic failure. Instead, they discover something more dangerous. The membrane contains microscopic pinholes allowing hydrogen and oxygen crossover. The porous transport layer has developed a thick resistive oxide layer across large sections of its surface. Catalyst particles that once measured only a few nanometers have agglomerated into inactive clusters. Electrical resistance has risen steadily for thousands of hours. Heat damage appears in patterns across the membrane structure. None of these failures happened suddenly. All of them began on day one, not because the operators made a mistake, because the cell was designed incorrectly before the stack ever turned on. And this is one of the biggest hidden realities in the green hydrogen industry. Most electrolyzer failures do not begin as operational problems. They begin as design decisions. That changes how engineers should think about electrolyzer systems entirely. Because good PEM electrolyzer design is not about assembling advanced materials into a stack and hoping they survive. It is about understanding how tiny non-uniformities evolve into massive failures over tens of thousands of operating hours. That is what separates laboratory performance from industrial survivability. And survivability is what actually matters. The hydrogen industry often focuses on efficiency numbers, current density, iridium loading, or peak stack performance. But industrial hydrogen systems do not fail because they were slightly less efficient on day one. They fail because gradients form. Temperature gradients, hydration gradients, compression gradients, electrical resistance gradients, flow distribution gradients. And once those gradients appear, degradation accelerates unevenly across the cell until one local region becomes the failure initiation site for the entire stack. This is why PEM cell engineering is fundamentally a systems discipline. Every component interacts with every other component. The membrane affects hydration. Hydration affects resistance. Resistance affects heat generation. Heat affects catalyst degradation. Catalyst degradation affects voltage. Voltage affects corrosion. Corrosion affects conductivity. And conductivity changes current distribution across the entire active area. Nothing inside the cell operates independently. That is the first principle every electrolyzer engineer eventually learns, or learns painfully. Let's start with the membrane. Because membrane failure is one of the most feared degradation mechanisms in PEM electrolysis. When people imagine membrane failure, they often imagine a sudden rupture or catastrophic tear. But real membrane failure is usually much slower and more subtle than that. Microscopic pinholes begin forming inside localized regions of the membrane structure. Hydrogen and oxygen begin crossing over internally. Purity slowly declines, safety margins shrink. Eventually, the system reaches flammability thresholds or shutdown conditions. But the truly important question is not, what failed? The important question is, why did failure start in that exact location? Because membrane degradation is almost never random. The failure locations themselves tell the engineering story. Many failures cluster near inlets, others cluster near edges, and both patterns reveal design mistakes. Near the inlet, hydration distribution becomes critical. Before water flow stabilizes uniformly across the active area, some regions experience temporary dehydration. A dehydrated membrane has higher ionic resistance. Higher resistance generates more localized heat. Higher heat accelerates radical attack on the polymer structure. And now, a tiny hydration imbalance becomes a long-term degradation accelerator. Over thousands of hours, microscopic chemical damage accumulates. Eventually, the membrane fails. But the real failure did not occur at 12,000 hours. It occurred during the original flow field design process. That is the hidden engineering reality. And then there are edge failures. Edge regions experience different mechanical conditions than the center of the cell. Compression loads shift near gasket transitions. Electrochemical environments become slightly different. Stress concentrations emerge. If compression is not distributed uniformly, the membrane experiences uneven mechanical loading for tens of thousands of hours continuously. This is why serious PEM stack engineering increasingly relies on finite element analysis for compression behavior. Because compression is not just a sealing problem anymore, it is a durability problem. And this is where the Renee Energy Systems framework becomes important again. PEM cells do not fail because one component is weak. They fail because coupled systems amplify small weaknesses over time. That distinction matters enormously. Now move deeper into the membrane electrode assembly itself. The catalyst layer. This is where some of the most expensive materials inside the entire hydrogen economy exist. Iridium catalysts are essential for PEM electrolysis because the acidic oxygen evolution environment is extraordinarily aggressive electrochemically. Few materials can survive there while maintaining catalytic activity. And this is where another hidden trade-off appears. The hydrogen industry constantly pushes toward lower iridium loading. For good reason, iridium is extremely rare. Global production is tiny. PEM scaling eventually collides with mining constraints unless catalyst loading falls dramatically. But reducing catalyst loading introduces another problem: durability. This is where laboratory optimization often collides with industrial reality. Smaller catalyst particles create higher surface area. Higher surface area improves initial performance, but extremely small particles are thermodynamically unstable. Over time, small particles dissolve and redeposit onto larger particles through Ostwald ripening. Tiny particles disappear, large inactive agglomerates form, active surface area collapses, and suddenly a stack that looked excellent during commissioning begins slowly losing performance year after year. Cell voltage rises, efficiency falls, hydrogen production declines, project economics deteriorate. This is why electrolyzer design must always target end-of-life performance, not beginning-of-life performance. That is one of the most important principles in industrial electrochemistry. A beautifully optimized laboratory cell that survives 2,000 hours is commercially useless for infrastructure expected to survive decades. And then things become even more complicated, because catalyst degradation is not controlled only by catalyst chemistry. It is also controlled by operating behavior. Startup and shutdown procedures matter enormously. Voltage spikes during transient operation accelerate iridium dissolution dramatically. During those spikes, catalyst material can dissolve directly into the membrane environment and redeposit elsewhere inside the MEA structure. And now electrochemistry, controls engineering, and operating philosophy become inseparable. This is why modern electrolyzer systems are increasingly becoming software-defined electrochemical systems. The operating algorithm itself becomes part of the durability strategy. Again, the systems layer returns. Now let's move to one of the least understood components in PEM electrolyzers, the porous transport layer, or PTL. Most people entering the hydrogen industry underestimate how important PTLs are. They look simple, but they quietly control gas transport, water distribution, electrical conductivity, thermal transport, pressure distribution, and interface stability all simultaneously. And this is where titanium enters the story. Titanium is widely used on the anode side of PEM systems because it survives acidic oxidizing environments relatively well. But titanium survives through passivation. That sounds good initially, until you understand what passivation actually means. Titanium forms titanium dioxide on its surface. Titanium dioxide is electrically resistive, which means the material protecting the titanium slowly destroys electrical conductivity at the same time. This is one of the great engineering paradoxes inside PEM systems. The material survives chemically while degrading electrically, and over thousands of hours, resistance rises steadily. Voltage losses increase, efficiency falls, heat generation rises. Now add another systems interaction. Compression non-uniformity changes contact resistance locally. Local contact resistance changes electrochemical potential distribution. Potential distribution changes oxidation behavior. And suddenly, poor compression accelerates oxide formation in exactly the regions already electrically weakest. That feedback loop matters enormously. This is why precious metal coatings on PTLs are becoming increasingly important despite cost pressure. Thin platinum or gold coatings dramatically slow resistance growth and stabilize conductivity over long operating periods. And this creates another major hydrogen industry tension: cost reduction versus durability. Because the pressure to reduce stack cost often encourages procurement teams to eliminate coatings, reduce thicknesses, simplify components, or lower catalyst loading aggressively. Those decisions may improve short-term capex, but they may destroy long-term project economics. And this is one of the deepest lessons in industrial hydrogen engineering. The cheapest stack is not always the lowest cost hydrogen system. Durability dominates economics over time. Now let's move to perhaps the most dangerous failure mode of all, thermal hotspots. Because hotspots create self-reinforcing destruction loops inside PEM systems. A partially blocked flow channel slightly reduces local water availability. Reduced water availability lowers cooling. Lower cooling increases temperature. Higher temperature accelerates membrane degradation. Membrane degradation changes resistance. Resistance redistributes current. Current redistribution increases local heating even further. And suddenly a tiny flow disturbance evolves into catastrophic membrane perforation. This is why PEM electrolyzer engineering is fundamentally about managing gradients before they become amplification loops. And this is where many next-generation electrolyzer concepts quietly fail. They optimize beautifully for efficiency, compactness, current density, or material reduction. But they leave too little tolerance for non-uniform operation. Industrial systems need robustness, not perfection. Because real-world operating environments are messy, flow channels partially clog, water quality fluctuates, compression shifts over time, operators cycle systems unpredictably, renewable energy inputs fluctuate continuously, temperatures drift, and systems that tolerate disturbance survive far longer than systems optimized too aggressively around ideal operating conditions. This is one reason industrial electrolyzer engineering increasingly resembles aerospace engineering more than traditional chemical engineering. Because reliability under stress becomes the defining design challenge, not merely performance. And this is where the Renewable Energy framework ultimately leads. Uniformity. That is the hidden principle underneath nearly every long-life PEM system. Uniform temperature, uniform hydration, uniform compression, uniform current density, uniform coating quality, uniform flow distribution. Every non-uniformity inside the cell is a potential future failure initiation site. The best PEM cells are not the ones with the highest peak performance. They are the ones with the smallest gradients. That realization changes everything about electrolyzer engineering. Now another critical principle emerges. Co-design. The hydrogen industry sometimes discusses membranes, catalysts, PTLs, flow fields, and cooling systems as if they are independent optimization categories. They are not. Membrane thickness affects hydration behavior. Hydration affects thermal distribution. Thermal distribution affects catalyst degradation. Catalyst degradation affects voltage distribution. Voltage distribution affects corrosion behavior. Everything couples together. This means real PEM engineering is no longer component engineering. It is systems engineering. And that distinction is critical as electrolyzer manufacturing scales globally. Because many companies entering the hydrogen market underestimate how tightly integrated these systems truly are. You cannot optimize components independently and expect the full cell to behave optimally over 80,000 operating hours. That is not how electrochemical systems work. Now layer renewable intermittency into this picture. Because future PEM systems increasingly operate alongside variable renewable electricity, that introduces constant cycling. Start-stop behavior, dynamic ramping, transient operation, and all of those conditions amplify degradation mechanisms differently, which means the renewable hydrogen era may require entirely different durability optimization strategies than traditional industrial electrolysis systems. Again, the future hydrogen economy changes the engineering itself. And this is why PEM electrolyzer engineering remains one of the most difficult industrial design problems in the energy transition. Because engineers are simultaneously trying to optimize efficiency, durability, cost, scalability, material usage, thermal stability, dynamic response, manufacturability, and survivability, all inside a chemically aggressive electrochemical environment operating continuously for decades. That is an extraordinarily difficult systems challenge. But understanding these failure mechanisms changes how engineers approach the problem, because the failures stop looking random and start looking predictable. The membrane did not unexpectedly fail, the catalyst did not suddenly degrade. The PTL did not mysteriously stop conducting. The hotspot did not appear. The physics were always there, the gradients were always forming. The degradation simply needed time to become visible. That is the real engineering lesson. And it may be one of the most important lessons in the entire hydrogen industry. The Because as electrolyzer deployment accelerates globally, the winners may not be the companies with the most impressive launch announcements or the highest day one efficiencies. They may be the companies whose systems survive 80,000 hours in the real world. If you are evaluating electrolyzer systems, stack suppliers, or procurement specifications for a real hydrogen project, H2 Hub by Renee Energy provides tools and specialist support for engineering due diligence, system evaluation, and project-level technology assessment. The link is in the description. Because in electrolyzer engineering, failure rarely begins on the day the stack shuts down. Failure usually begins the day the cell was designed.